Okay, thank you everyone for returning on time. We're going to continue our discussion this afternoon about emerging technologies and other technology-related topics. Our first speaker is going to give us an overview of emerging technologies in the whole field of high contrast imaging. Good luck.
Yes. So thank you. I'm going to talk about the emerging technologies. There are many emerging technologies. That's why this talk is a little bit like an octopus talk. I'm going to go in all kinds of directions. I'm very sorry for some incoherent jumps between technologies, but it was difficult to make a coherent story between all the different things that are happening in the world. Yeah, so I will start off with an animation. So this is a video of I don't know how many years of observations of beta pictoris b. But one of the things that I really like is if you look at these two circles, then you can see the outer circle is the inner working angle we had at the beginning of observing beta pictoris b. And the new circle is the one on the inner edge. That's the new inner working angle that we have with current generation instruments. And you can really see in this video this large improvement of inner working angle that we've already achieved in over a decade of our work together. So I think that's really impressive. And now we just need to do it again to really go to the smallest inner working angle. So it's already quite a big improvement. So we're quite far away from what we actually want to achieve. Oh, wait, I accidentally clicked the button. So, for example, with the extremely large telescopes, which includes GMT and ELT in this case, we're trying to aim for contrasts of 10 to the minus 9 and 10 to the minus 8 at 10 to 100 milliarc seconds. So you can see that roughly in this plot, where here we're at 10 milliarc seconds. 10 and 100 milliarc seconds. We're aiming for 10 to the minus 8 and 10 to the minus 9. And of course, with HWO, we're trying to go for about 10 to the minus 10, or as we saw this morning, we need to go deeper. But we're still quite far away from these contrast limits and from the actual theoretical limits. So what do we need to improve? Well, many things. So first of all, we need to work on the adaptive optics, more sensitive wavefront sensors, faster AO loops, better control algorithms. We need to improve our coronagraphs, higher throughput, smaller inner working angle, coronographic wavefront control, such as PSF stabilization, dark hole digging, and maybe new kinds of coronagraphs where the wavefront sensor is integrated into the coronagraph itself. And on the end, we also want to have post-processing methods that actually reach photon noise limited residuals without having systematics in them. So we have sort of these four things that we need to work on. I'm not going to discuss all of them because the first one has already been covered by Marcus Kasper yesterday, but I am going to discuss the other three. So as you can see, I have a lot of topics to cover, so prepare for a ride. I'll start with the coronagraphs. This is a recent overview and a proceeding from Ras Belikov showing the throughput of several coronagraph designs, I think on the DST, with their achieved contrast here on the right. So this is the contrast that was achieved. The mean, I think it's the mean contrast within the dark hole. And you can see the combination with throughput. What is very clear here is that we are not yet at 10 to the minus 10. There's also a large gap between the optimal throughput and the actual achieved throughput for these coronagraphs. And many talks this week mentioned the importance of having enough throughput. So really high throughput coronagraphs is really very important, especially if we need to achieve another factor of 10 to 100 in post-process contrast, then you need to build up signal. You cannot lose precious photons. But what we do see is that there's a class of coronagraphs here that has really high throughput and also much smaller inner working angle than the others. So for the rest of my talk, I'm going to discuss these coronagraphs and the perform, like, and how they have improved over the past years. So I'll first start with the vortex coronagraph. A lot of you have worked with it, so I'll go through it a little bit faster. So we start with a clear aperture. You have your PSF in the focal plane. You put it through a vortex spiral phase mask. Then in your subsequent LEO plane, you see a nice dark area. You block it with a LEO stop, and you're left with nothing. That's all super great. Of course, we don't have clear apertures, or apertures like this. However, I was very pleasantly surprised when I saw this paper come out a couple weeks ago, where they showed the EAC 4 and 5 designs, which are off-axis designs, because that works very well with this vector vortex, with the vortex coronagraph. There's only one downside still. You have the segmented apertures. So you have the segmented PSF going through the vortex again, creating the subsequent LEO plane, and you can already see that there is residuals because of the segment gaps. So that leads to strong residuals. But luckily, there are now also solutions in apodizing your entrance pupil plane that actually can solve this. So we have phase apodized solutions and amplitude apodized solutions that can create dark regions. So for example, here you can see a very broadband solution, and you can compare the PSF or the coronographic residuals between the not apodized version and the apodized version. So we can actually deal with segment gaps pretty easily. It's not too difficult. Central obscurations are difficult. But that's why it was so great to see that the EAC 4 and 5 don't have a central obscuration anymore. So that's awesome. So how far along are we in the lab? So apparently this is already a little bit older. So I think we're already a bit further ahead in contrast. But these show results of the effect of the vortex coronagraph on the DST. And it results in about 10 to the minus 9 contrast in the 10% bandwidth, and about 6 times 10 to the minus 9 in 20% bandwidth. And in this work, it was said that the main limitation is really in the mask manufacturing, so in the vortex mask. So this morning, you've already seen a nice talk from Rico that showed some of the results that we have for improving these geometric phase vector vortex coronagraphs and the manufacturing with patterned liquid crystals. And then after me, somewhere in the afternoon, we'll have also a nice talk by Skylar. And I'm hoping that he's going to talk about meta-surface vortex coronagraphs, because that's what I'm showing now. So if you're not doing that, then I'm a little bit, disappointed. So this works great for HWO, but will it work well for the ground-based telescopes? Well, answer is probably not. So here you can see the apertures of the ELT. So for the ELT, you might think, well, we could come up with a ring apodizer. But then when you look at GMT, it's hopeless. Vortex is really, it's sort of out of the, it's really not an option. So these two actually are really not very suitable for vortex coronography if you want to achieve high throughput. So with the ELT, you can make a deep contrast vortex coronograph, but it will eat into your throughput. You might have 10 or 16% left after you add the correct apodizers. And that's not a lot of throughput. So also, what I'm also interested in is in pushing the inner working angle. And the ELT and GMT diffraction limit at 1 micron is about 5 to 8 milliarc seconds. And if I look at the plot again from Marcus, and we look at this figure, then we can see that actually at the 1 to 2 or 3 lambda over d, there's actually still planets left that we can look at if we have a 1 lambda over d inner working angle. So we can actually extend the planet population if we can push in the inner working angle. And also for HLBO, it's very important to go to 1 lambda over d because of the limited aperture diameter. So one of the coronagraphs that has been promised to do this kind of science is the PIA, well, I will say it once, phase-induced amplitude apodization complex mass coronagraph, or PIA-CMC. This coronagraph has an inner working angle of 1 lambda over d, or even smaller. It is very complicated because you can see we don't only have like a potential apodizer, we also have aspheric lenses that create an apodized pupil. Then we go to a focal plane and we have a small phase shifting mask. Then we have a Leo stop, and then we also have inverse aspheric optics to restore the geometry that was messed up by the first set of forward PI optics. And then in the end, we have our final science focal plane here. I have to point to a weird direction to get this pointer to work. So here I'm showing some of the results that we had by implementing the PICMC on the MagioX instrument. So the PI optics create strong off-axis aberrations. So this is just the normal PSF. And then here we created reference PSFs using our DM. So with the DM, we can modulate and create copies of the PSF. We put in this forward PIA, and then you can see the off-axis aberrations. So the on-axis PSF is nicely apodized, but the off-axis PSFs turned into pineapples. And we don't want pineapples. So, but luckily, if we add this inverse set of PI optics, we can actually restore the quality. And we actually get nice off-axis PSFs back again. This also was tested on Sky, of course, and I will show that a little bit later. We are currently trying to manufacture the face masks using a nanoscribe, so that's a 3D nanoprinter. We are currently achieving about 50 nanometers peak-to-valley error on these arbitrary grayscale patterns. So it's actually it's pretty good. Well, if you had the opportunity, you might have seen her poster. It's now gone, but I will still refer to it. So I think an exciting result here are the actual throughput measurements. So here you can see this in black, the simulated throughput curve, and in blue, the actual measured in-lab throughput curve. And what we have actually achieved now is an inner working angle within 1 lambda over d. So that's great. So these coronagraphs can actually do diffraction, like imaging at the diffraction limit. And it also works on Sky. So here's our on-Sky PICMC data. And if we zoom in the center, you can see that there's something going on. If I blow it up a little bit, you can see that there's actually a companion star here, separated by about 40 milliarc seconds, which is about 1.1 or 1.2 lambda over d on MagioX. So we can really push the inner working angle to very close separations. Again, you could have seen this on her poster. But now we have a question, can we actually do better than PICMC? And how close to the actual fundamental limits are we? So to answer that question, we first need to know how far away are we from this fundamental limit, and what is the fundamental limit? So to answer that, I will teach you all quantum mechanics. So if we have 2 point sources, or 2 stars, each of these creates an electric field. They create wavefronts that propagate to our telescopes. And in this quantum mechanical framework, each of these can be attributed to with a coherent state. So here we have the wavefront now being a nice, where's the pointer? There it is. Coherent state psi1 and psi2. So if we want to know how these 2 add together, we need to go to something called the density matrix, which is this thing. So here we show how you can describe it, 2 incoherent sources in a quantum mechanical sense. So this is called a statistical mixture. Okay, that was all the quantum mechanics you had to learn. So now we know everything to do this fundamental limit. So luckily, we don't have to do it ourselves. Other people have done it. There's this field of quantum metrology. And in quantum metrology, they actually have figured out how to determine what the maximal information is that you can get out of a certain quantum state. So how do they do that? You have your state, you add a little bit of a delta state, then you have your fancy system, and then you get an observable with a delta observable. And what the framework of quantum metrology does is it optimizes your optical system over all potential optical systems to find out which one maximizes the signal to noise, which one maximizes the information content. Setting, you lose the information about the optical system itself. You only know the maximum, but not the system. So it does give you the upper limits. So what we actually calculate is called the quantum Fisher information, which is related to the quantum Kramer-Rao bound, which, if you're familiar with this kind of terms, it's just the equation for classical Fisher information and classical covariance. The only thing that you have to change is put a Q in front of Fisher information, and then you're done. What you have to remember more information means lower covariance per photon. So more information is more better. So optimal coronagraphy, you can actually do that with mode splitters. So here we have the electric field of our star summed over all these special pupil plane modes. So these are the Zernike modes. We typically use them to describe phase errors, but you can also use them to describe electric fields. And here you see the corresponding focal plane images. So you can see that here for piston, for example, we have the normal Airy pattern, and then for tip and tilt, you have these modes that sort of split up in two lobes. And then we, of course, also have higher order modes. So what do? We make a device called a SPADE, or a spatial mode demultiplexer. This is sort of like a spectrograph, but instead of splitting wavelength, it splits modes. So you just get points out, and the intensity of each point corresponds to a particular mode. So this is called a SPADE, and if you combine them with single photon detectors, you can achieve these quantum optimal bounds. But you need to choose your correct mode basis. So for every observation, you have an optimal mode basis. Here you can see how well or what the information content is for the separation between planet and star as function of separation on a logarithmic scale. So this was work done by Nico Deschler at U of A. And here we can see the Fisher information, the normalized Fisher information versus the planet separation for several coronagraphs. So QFI here is the fundamental limit. Then we have SPADE, so that's the one that I just showed. We have the perfect coronagraph, which was something we came up with 20 years ago. Here's PSCMC and the vortex coronagraph. What you can see here is that SPADE saturates the QFI bound for estimating planet brightness and position, and that means that it's a quantum optimal way of actually doing the detection. However, PSCMC and the vortex coronagraph are also within a factor 2 of the fundamental limit, and even outside 1 lambda over d, they're actually within 20 or 30%. So they're actually really close. One thing that's weird here, you might have noticed this, is that you have like a really high information content here, which is at 10 to the minus 2 lambda over d. So super resolution things. So is this special? Yes. Is it useful? No. Because often these QFI measurements are done for point sources, and we all know stars are not point sources. So if we calculate the response as function of brightness of the companion and as stellar angular diameter, we can see the moment we add a 10 to the minus 4 lambda over d point source, so 10 to the minus 4, for faint planets, the QFI, which was first at 1, has completely collapsed and it's gone. So any amount of spatial extent completely destroys sub-lambda over d information, which is logical because you have these, you have that information, or you have the crosstalk. So this eigenbasis of the telescope that we optimized for point sources does not work really well for deep contrast and resolved stars. Is there a single mode basis? The answer is no. Here you can see the Fisher information, which is approximately the signal to noise squared, where we have the throughput of the planet squared divided by the throughput of the star plus the noise of the planet. So this is a standard SNR equation. One of the things is you see the planet coming down in the bottom, and that means that the planet flux actually matters quite a bit. You cannot arbitrarily null your star, because at some point the planet is actually the dominating noise source and not the star. So that means that this is work done by Yinzi, that the optimal mode for a planet of 1 lambda over d, for example, stellar diameter of 0.2 lambda over d, actually depends strongly on the contrast of the companion. You can see here from the left to the right that this mode actually changes. There was a poster. Maybe you have seen it. I don't know. So what mode sorters have been implemented? Because this is not super new, or at least people have done it. So there's going to be a talk today about doing super resolution imaging with photonic lanterns today. So photonic lanterns are mode sorters. So here you can see how it works. You have a fiber with, on one hand, a multi-mode input, and on the other hand, we have several single-mode outputs. And the modes here, you can see they look sort of similar to the Zernike modes, but not completely the same. But they're very similar, so it works quite well. Another way was the talk from this morning, the astrophotonic integrated circuits. It's also a mode sorter that implements this kind of work. So if I need to summarize things, is that we're actually developing coronagraph architectures that approach these quantum optimal bounds. We're currently still a little bit manufacturing limited, but I think we are really pushing on the development of these kind of devices, and hopefully in a couple years we are there. So that means these are optimal. That means we also, like, hopefully 20 years from now, we don't have to do anything anymore, and it's just an engineering problem and not a conceptual problem anymore. Okay, coronagraphs solved. Now we need to go to coronographic wavefront control. It consists of a lot of different things. Main problem here are non-common path aberrations, because they limit our achievable strail, they cause stellar leakage into the coronagraph, and they slowly change and are difficult to post-process. They're really, really annoying. What is the origin of NCPA? It's because we have optics in different paths. So typically, we have a system where the light from the telescope goes to a certain wavefront sensor that sees a certain set of optics, but at some point we split it off and it goes into the coronagraph system. But you can see there's many different optics that the wavefront sensor doesn't see. So we know from the beginning that there are going to be wavefront errors. And that's why it's also crucial to incorporate wavefront sensing into the design of your coronagraph. Your instrument also needs to be able to correct for wavefront errors, so you need a DM. And this also impacts optimal mode sorters, because the optimal mode sorter will depend on the wavefront states. So not only on finite diameter, but it's also the wavefront errors that you expect will impact the optimal mode sorter. So it's a very complicated problem to get the optimal mode basis and the optimal sorter. I will not discuss that because we have not solved it. One of, I think, the interesting topics is merging coronography and wavefront sensing, where we try to make the where we try to push this wavefront sensor instead of making it separate. It's really part of the coronagraph itself. Oh yeah, now remember what I want to say here. That was the simplified coronagraph setup. In the more complicated one, this is what we actually want. I see that the color has faded a little bit, but you can trust me that there is light. So this is now a schematic of the MAGIOX instrument, where we have a separate deformable mirror for coronographic wavefront control, and every part of the optic becomes a wavefront sensor. So we have our focal plane mask that reflects light. We call that the focal plane low-order wavefront sensor, the FLOVIS. And then we have our LEO stop that's also reflecting light, and that goes to this camera. And I'm very happy that people have taken up on the name that we use for it, which is the YOVIS. So I hope that everybody will keep with that. But I think this is a fundamental architecture change for ground-based instruments. And it really helps us push the performance to include this separate coronagraph DM. And MAGIOX is doing extremely well now with this new coronographic DM. Here you can see the Magellan telescope that is being used at. Here you can see MAGIOX in better times. It's now a little bit, the color has faded a little bit. It's here in Chile, and we're currently doing lots of great science, all at optical wavelengths. For example, here we have beta Pictoris B at Z-band, HR8 4796A in G-band, PDS70B in C, and some just interacting stellar binary. So this new DM has been characterized and integrated into MAGIOX by Jay Cuny. Here you can see it. It's beautiful. It's great. It's helped us a lot. And now we can actually do all these different kinds of wavefront sensors very efficiently. So first, this lower the wavefront sensor. We're currently using a optical model-based approach. So here you can see the measurements, our optical model, and the residuals. And we can perfectly match the FLOVIS data. So this is pure physics-based, and allows us to really quickly switch between coronographic masks if we need to load in a new model. This is the video showing its performance. This was in lab, not on Sky, because I couldn't find the on Sky video. But here you can see if we close the loop, it works quite well and it restores the PSF. One thing that we forgot here is to put in the LEO stop. So this is not a very good coronagraphic image, but it works. We can stabilize 9 modes at 8 kilohertz. So this is a lot of fun. All work done by Matthijs. So now on to YOFIS. So YOFIS, you can do several things, but I think one of the exciting things is to actually turn it into a Zernike wavefront sensor. So this is a project that I'm doing with Dwanil Patel, who's a master's student in my group. Here you can see the PA-CMC coronagraph layout again. But now we're making it complicated because now it becomes PA-CMC Zernike wavefront sensor. So it's become a longer name. What we now do is to have the focal plane mask, and we make it actually, we give it 2 functions, both a wavefront sensor function and coronography function. And then here, after the focal plane mask, we split it into two paths. One is the coronagraph path, and the other one is the wavefront sensor path. And with that, we actually have merged these 2 together. And how we're making them is with meta surfaces. So here, you can see a meta surface schematic of how it looks like if you look at all the pillars together. And here's an actual SAM image from the US Santa Barbara group. They're really amazing. If you want to build things like this, contact them. They're great. No charge. The fundamental thing of meta surfaces is that it's sub-wavelength. So you need to make them really, really small. But then you get some special interaction with the light. And with this, we came up with a design where in H-band, this is a coronagraph, and in J-band, it's a Zernike wavefront sensor. And that means that you can, if you look at your science camera, you have a nice coronagraph. Here we have a Zernike wavefront sensor, and here we have those pesky NCPAs. But if we turn the AO loop on, close the loop, correct for everything, we actually have a nice flat wavefront sensor image. We have corrected for the NCPA, and there's no wavefront errors anymore. So that's great. Okay. Final part of the wavefront sensor train is the science camera, where we want to do dark hole digging algorithms. So one of the first things that we tried with MagUX is EFC, or my flavor of EFC, IEFC. You should read my paper if you want to know about it. I'm not going to explain in detail, but here in this video, I'm showing that we can nicely and neatly dig a dark hole. This is with the classic LEO coronagraph, and this is also at the time when I did not understand very well how to do this, so the contrast is not super impressive, but at least you get a bit of a feeling of what happens. You just dig away the quasi-static speckles. And one of the things I want to highlight here is that you do an offline, off-sky calibration and use that on sky, because this was a misconcept that appeared somewhere in the community, is that I only do one calibration on off-sky and use it on sky. So here you can see some on-sky results. I did some high-pass filtering to get rid of the wind-driven halo, and that also enhances the quasi-static speckles at the inner working angle. So this is before EFC, and this is after EFC. And after EFC, you can really see that those quasi-static speckles have been nulled out on sky, and you can see a 10 to the minus 4 injected companion at 60 milliarc seconds. So this paper is in prep, and it's been in prep for a year and a half now. I'm a little bit behind on writing it. So can we do more wavefront control? Yes. I also want to say that we are not the only team that is doing these on-sky EFC experiments. It's also at Sphere. They're really doing very well, and we've also seen this week that now the Spiders instrument is doing this kind of dark hole digging. And I think that is also a new technology that is now coming online that wasn't here yet during previous Spirit of Leo, or at least so well spread. So another interesting thing is to use the self-coherent camera, which is now also going on sky at multiple instruments. George gave a nice talk about it this morning, and Elena also made a self-coherent camera for MagUX. So I'm going to show some of those results. We went on sky, I think it's already a year and a half ago, in November 24, where we manufactured a tilted classic LEO coronagraph, again with a nanoscribe. And here you can see the data from that coronagraph. It's a bit difficult, I know, but if you look very closely, you can actually see that the speckles from the on-axis object are fringed, and they are very small compared to the off-axis companion. You can really see the difference between the on-axis light that's fringed and the off-axis light that's not fringed. This is also a screen grab, which shows you how excited we were. We also did dark hole digging with it, I think April 2025. So here you can see our nice dark hole with the SEC. You can actually, you see it by seeing the difference between the top and the bottom. Dark hole digging on sky at visible wavelengths is difficult. That's what I want to, that's a message you need to remember. We're currently going for, the goal for 2026 and 2027 is to see if we can merge the PSEMC with the SEC to actually get also wavefront control and correction capabilities at 1 lambda over d. So that will be the final goal of this project. So, luckily, I'm still on time. Great. I was very afraid I wouldn't be. Last thing that I want to mention is advances in post-processing. So this week, we have seen many, many talks, actually, about physical optics-based forward modeling of your speckles. And I think that is really going to be the future of high-contrast imaging. What we're doing here is we have our instrument, and we have our instrument model. And with that, we're trying to fit or figure out where all the speckles come from our science image, and see if we can make a model image that reproduces those. So with James Webb, it's not easy, but relatively speaking, it's easy. Because James Webb is quite static, and it doesn't have an atmosphere. If you want to forward predict everything that the atmosphere does to your telescope or to your images and to your mental health, then you need some wavefront sensor images. So we have a wavefront sensor in ground-based instruments that are running at really, really high speeds, so 2 kilohertz, 4 kilohertz. So you get thousands of images per second. And all of these predict the stellar speckles at the focal plane. So if you have a very advanced digital twin of your instrument, you can actually feed these wavefront sensor images into this digital twin to predict the atmospheric speckles. And if you can do that, then we can take our model image, subtract it from the science image, and we have our nice post-processed image where we can now detect planets. It's a little bit trickier than space telescopes because of this. So we need to adjust the digital twin model and the forward model to include quite a lot of components. I don't know how much data it takes to forward model James Webb observations, but if you want to forward model a 2-hour MegaOX observation, then you need about 2 terabytes of GPU memory. And it's that data set, that's the size of the data, that makes it complicated for ground-based telescopes. If you were there, you might have seen Joseph Long's poster where some of these issues were addressed. So now let's suppose that we can do this in this magical world in the future where all my problems are solved. Then it's going to be great, the future. Here you can see some very preliminary ELT PCS simulations that I did. So I simulated an end-to-end model of PCS. I simulated 1 minute of data with a wavefront sensor and an AO loop running at 2 kilohertz. Then my science observations were done in J-band with a spectral bandwidth of 1%. I assumed an end-to-end throughput of about 30% for an imager. I have a total exposure time of 60 seconds, a planet contrast about 3 times 10 to the minus 7 from Van and al. 2024. We can discuss whether or not that's correct, but that's what I picked. And then, like I said, we have this full end-to-end AO simulation. This took my laptop a long time to run, but in the end, this is the image that I got out. And here you can see Proxima Centauri be injected at 8 locations. And you can see that we detect 7 out of 8 of these injected planets, and the one on the right is a bit, I'm not sure if I would call it a detection, but most of them are detected at what I call 5 sigma, and maybe after the talk this morning it might not be 5 sigma, but For me, it's 5 sigma. So this telemetry-based post-processing method actually achieves the photon noise limits. So here you can see the raw contrast curve in blue. And then in orange, you can see the standard deviation of the raw contrast. So that's sort of the speckle noise limit. Then based on the raw contrast, we can actually predict what the photon noise limit should be, which is this red line. And now I've realized, I made this figure very quickly. And you might see that I made a very, very fundamental mistake. I mixed red and green. So I'm very sorry for the colorblind people. But they're the same line anyway. Both of them show that we achieved the photon noise. So it's all good. And if we're reaching the photon noise, that means that longer exposures lead to deeper contrast. And this method can also be used to retrieve the NCPA errors, because that's fundamental in the process. It's a very fancy way of doing phase retrieval. I have to say here is that this only works on fainter objects at the moment. So Proxima Centauri b is faint enough that this works. On bright stars, we are actually hit by a wavefront error type that I did not expect, but it's nonlinearity of wavefront errors. Typically, when we have a wavefront sensor, it has a certain spatial frequency that it measures. So there's a maximum spatial frequency content that's part of your wavefront sensor. All the wavefronts are the spatial frequencies outside of that cutoff frequency are not measured by your wavefront sensor. And that means that you cannot forward model those. One of the problems is that if you have wavefronts or spatial frequencies that you cannot measure, there's also spatial frequencies that are close to it. And those two create beating frequencies in the first second order term. And you get the doubling frequency and the difference frequency. And this is an effect that we have also seen in space test beds, where we call frequency folding, where you actually have light folding back into the dark hole from higher frequencies. And the same thing happens here. So all the frequencies that you do not measure with your wavefront sensor actually create nonlinearities in your focal plane and limit your contrast. So for a brighter star, and I estimated that with the current set of parameters, that for a 5th magnitude star, you're actually limited by these second order effects in this telemetry-based post-processing. So you don't achieve the photon noise limit yet, but you do achieve this limit that actually scales down very rapidly, because they're created by atmospheric speckles, which change at the 5 to 10 millisecond level. And if you're GPI at the 1 millisecond level, then you can actually very quickly beat down this limit again, but it's just a different scaling. So instead of photon noise scaling, you get Greenwood frequency scaling, which is still nice. So it will still go down, but a little bit slower than photon noise. So to get these methods to really work, we need to have better detectors. So this is something that I added very late in my presentation. So sorry for the quality. I think one of the exciting things that we see in emerging technologies are quantitative CMOS cameras. These are CMOS cameras that are using CCD technology to create backthins, to create very high QE pixels. And they also implement up-the-ramp sampling, what we typically use in infrared detectors, but then invisible CMOS detectors. That actually allows us to what they call, they were, I think, not allowed to call it photon counting, but they call it photon resolving, because you can actually see in the histograms that we're resolving individual photon counts. And that's because the read noise of these cameras is 0.2 or 0.25 electrons RMS, which is really, really small. And if we look at these photon transfer curves of the signal to noise, we can actually see that for the quantitative CMOS cameras, they're in a large fraction of photon flux regimes, they're actually doing better than EMCCDs. In the low flux regime and long exposures, EMCCDs are still doing a little bit better. But then if we go to high frame rate, then we see that they're almost outperforming EMCCDs all times. So I think this is a really interesting development that we now have these quantitative CMOS detectors. And I predict that maybe 10 years from now that nobody uses EMCCDs anymore. But maybe I'll have to go back on my word 10 years from now. I don't know. I actually think that these are very exciting. Another set of detectors that are exciting are MKITS detectors. which we are currently developing at Eschon in the Netherlands. And here you can see something that we want to propose for PCS, where we have a MKITS chip that does spectrally resolved data, so we can actually measure the photon energy, and we get wavelength-dependent image reconstruction that we then can use for active focal plane control and coronagraphy, and we can use it at the same time to analyze the spectra of the planets. No detector noise, fast readout, I think strong contender for future detectors. My ideal architecture, everything becomes a wavefront sensor, everything goes into the model, and we predict things as best as we can. And if that all works, we will use the future GMT and ELT much better than the current generation of VLT. We estimate that our exposure time gain, so how fast can we achieve the same signal to noise, for example, for ELT will be about 625 times faster than the VLT. So what the ELT can do in one night takes the VLT 2 years if we implement this technology. So I think the future is extremely large. Thank you.
Yeah, wonderful talk.
Thanks, Niyati. Thank you for a great talk, Sebastiaan. I have so many questions, but I'll try to narrow it down to a few. First of all, you mentioned one of the many wavefront sensors is reflected off of your LEO stop, and you wanted to integrate the Zernike wavefront sensor into that. Do you have a phase shift on top of a reflective LEO stop?
No. So for this one, it's this type of it's this thingy, this one. Yeah. So here we make I now put in a beam splitter, but this could be a reflective LEO stop beam splitter. So this is the LEO stop. These two things go together. That's the reflective LEO stop.
And then you have a separate Zernike wavefront sensor.
No, I mean the mask itself. It's a dual-purpose mask. It's sort of similar to what Kat's going to talk about later today.
Okay, that was going to be nice.
But then instead of having a Zernike wavefront sensor in reflection, it's a Zernike wavefront sensor in transmission, together with the coronagraph in transmission.
Right, so my other question was going to be, have you quantified the types of improvements you can get from running all of these wavefront sensors at once by turning one off and then seeing what happens and then like separately? Because I mean, maybe you said that already, but I didn't quite see how much it's adding to do all of these at once.
So you have to choose and pick a little bit, because depending on the type of coronagraph, you have different low order wavefront sensors. So if you have a reflective mask, like a occulting mask, we can use this one. But if you have a phase shifting mask like PSCMC or vortex coronagraph, there's no light that's reflected. There's only a phase shift. So that means for those, you need to use the reflective LEO stop. Okay. So it depends really on the type of coronagraph you have, whether or not you use this one or you use this one.
But they're not simultaneously being used.
Sorry?
They're not simultaneously being used for any of
No, because you only have one coronagraph on at the same time.
I was just wondering if that was possible. And,
yeah, probably, but not very efficiently.
Thanks, Sebastiaan. That was amazing. So ideally, you not just want to dig a dark hole with EFC, but you want the dark hole to be sustained and not degrade, and also any residuals to be temporally correlated. How important do you think something like spectral linear dark field control or spatial linear dark field control may be?
I don't know. We just dig dark holes constantly. We don't dig a dark hole and then keep it. We just try to constantly stay digging the dark hole. So we don't need to use other methods to stabilize the dark hole. We could maybe do it, but we've not seen big reasons to do it. Because at visible wavelengths you have a lot of light. We're not limited by the photon noise of the quasi-static speckles, which is why you would use linear dark field control. We're limited by the amount of time it takes us to integrate through the residual wind-driven halo at optical wavelengths. So I think at optical wavelengths you're not limited by those effects.
Raz Belkov, NASA Ames. Awesome talk. 2 quick questions. Are quantum optimal chronographs essentially the same as classically optimal coronagraphs, or are there scenarios where quantum optimal leads to a different solution?
Quantum optimal coronagraphs are actually, well, I mean, they're the same, sort of, because you can actually describe it completely also with classical physics, but the way to do the optimization and to get the correct modes out is difficult with classical techniques. So with the quantum mechanical approach, it's actually easier to do the algebra, which is what the quantum mechanics mainly gives us. It's better techniques. I only have 3 seconds left. If you can look here, you can see that the spade is actually better than the perfect coronagraph. And that's because the piston mode also contains information. And usually we reject the piston mode, but the piston mode has information. So if you have more questions, catch me at the next coffee break or tonight during dinner. I'm here to entertain you all day. Tomorrow I'm flying out.
All right, let's thank Sebastiaan again for a wonderful talk.